Well, here we are. We are at the end of the class, the final section to cover, the last section of chapter 7.5. And in 7.5, we're going to again look at vectors, which we introduced in 7.4. But in 7.4, the vectors were simply a direction and a length of an arrow floating somewhere in the plane. And so what we're going to do here in 7.5 is we are going to give an algebraic interpretation of vectors. And basically, the way we do that is we attach these vectors instead of loosely floating around in the plane. We attach them in the XY plane where we have a coordinate system and points, XY coordinated points. And we have all vectors originate from the origin. And then as we do that, we then see what it would look like for those vectors in an XY plane starting at the origin to do the operations that we defined already, like addition, subtraction, scalar multiplication that we defined in 7.4. We see what would that look like if these vectors were in the XY plane. And then we finally define a couple of new operations as well, like the dot product. So that's what we want to do in this final section to finish up our work in this trigonometry class. So let's begin. So the algebraic interpretation of the vector u, say that looks a little better. A vector with its initial points at the origin is called a position vector. And a position vector u with its endpoints at the point a comma b is written, and then they have, instead of parentheses, they have these sort of angled brackets to show that we're now talking about a vector instead of just a point. And so the vector a comma b. And so we have their notation from before, just a bold u. And now that's getting replaced with the vector AB, where the coordinated values AB are the X and Y values of where the vector would finish, where it would terminate. So this is the terminal point. Terminal point is what we refer to this place when we before talked about sort of a starting point and a finishing point of a vector. The terminal point is now AB, and the originating point of the vector is always the origin. And so we can see in the image here that this vector u, which normally would just be a blue arrow in a plane that started on the left and finished on the right, now starts at the origin, and the place that it finishes, we will use the coordinates of the point where it finishes to label the vector as the vector AB. Okay, so this is now how we give an algebraic interpretation of a vector. And so then we're pointing out that the numbers a and b are the horizontal component and the vertical component of the vector u. Since the vector now starts at the origin and finishes at AB, and A is the X coordinate and B is the Y coordinate of where it finishes, that means the point where it finishes has a height of the Y value B and a horizontal translation of A from the origin, which is the X value of the point. So then additionally, we can now, before we sort of imagined the slope of a vector, but we can actually, attaching the vector at the origin, imagine that the angle theta is the angle of elevation of the vector u, or as we may now refer to it, the vector AB. And so this is all diagrammed here, so we can try to sort of see the original vector as well as where it finishes and the angle that it travels on from the origin to arrive at that terminal point AB. And also we can focus on A and B being the horizontal and vertical components, and that we can also see this forms a right triangle, so that any vector when starting at the origin forms a right triangle at angle theta, to help us sort of see how the theta comes into play inside a triangle using our trig functions, as we will do a little later. All right, so now let's revisit some of the things we introduced about vectors. For example, the magnitude, which we had those absolute value bars around the notation for the vector u to indicate magnitude. Well, now if we think about the vector again finishing at point AB from the origin, well then the magnitude of u is the horizontal of this triangle, the length of this horizontal side of this triangle. And so by the Pythagorean theorem, that's the square root of a squared plus b squared. And so if we are now going to annotate vector u as a vector that finishes at the point AB, then the magnitude of u will be this square root of a squared plus b squared. And similarly, we can think about this angle theta determining sort of the direction of u. And we can express that in terms of those A, B values of the terminal point, because we know that the direction angle theta would satisfy that the tangent of that angle is opposite over adjacent or B over A, where A is not 0, because then obviously it would be undefined. In any event, so this allows us to now think about this new angle theta and the new point of finishing AB, and how we can now talk about the angle and the magnitude of this vector in terms of the values AB, which are the terminal point of the vector. So again, they're just setting this all up so we can then work with vectors in this new format. And then we can do addition, subtraction, scalar multiplication, and other things as well, all in terms of the terminal points of the vector. So they have this first example of using these two sort of formulas that they just gave us. And so first of all, if they give us this vector u, which is in this case 3, -2, and we have in the picture, you can see the blue vector u, it finishes at the x value 3 and the y value of -2. And so then we can look at this vector and think about what theta would be. And again, theta starts from the x-axis and rotates counterclockwise until you land on the vector, just like we had with points of circles when we were defining tan functions. And we can say, what is the magnitude and what is that angle theta? So the magnitude, we just do square root of a squared plus b squared. So they do that here. And that gives us the square root of 13. So that's how long the u vector is. It's the magnitude of the u vector. And then to figure out the theta there, we initially can set up the relationship that tan of theta equals b over a, which would be -2/3, as they do here. And then trying to get that angle theta, we can take the inverse tangent of both sides, so that theta equals inverse tangent of -2/3. But the inverse tangent, when we do that, the inverse tangent always produces results that are between pi/2 and -pi/2. And we know that we want our answer to be a positive theta that finishes in quadrant 4. So the inverse tangent produces, in this case, -33.7 approximately. But knowing in advance that that's going to be a quadrant 4 angle by using a negative degree angle, so this is where we would get tan inverse of -2/3. Knowing that that would give us this angle here, in a negative direction. And instead, what we want is the positive counterclockwise rotational angle. Then they immediately say we can get that by adding 360 to the result of the inverse tangent. So they add 360 to the result of the inverse tangent, and then that gets the theta as we want to define it and describe it as being counterclockwise from the x-axis with a positive measurement. And in this case, that's 326.3 degrees. So with this described relationship where we know tan of theta equals b over a, and we know we want theta to be positively rotated from the x-axis, that we can then put these two formulas together and produce the magnitude and the positive counterclockwise rotational theta measurement of the vector. We can get those from d squared of a squared plus b squared, and also using the relationship that tan theta equals b over a, and then we can use inverse tangent and get the correct angle measurement with an addition of 360 if needed. So that's a good example one to illustrate how we can now take a vector expressed as a comma b, just an x and a y value, and we can translate that into a magnitude and a theta measurement for that vector. Okay, so above we had a recognition that when we place theta into an xy coordinate system and define it as an AB, that the A and the B are the horizontal and vertical components correspondingly. And so if we're given A and B, we know those immediately. If we're given vector in the form of AB, then we know what A and B are, and we can use A and B to find the magnitude and the angle, as we saw in example one. So in example, in the next example, we're going to consider the opposite direction, where instead of being given A and B and finding the magnitude and theta, what if we were instead given the magnitude of the vector and the angle theta? Then how would we find out the terminal point AB to express the vector that way? And so to do that, they give us this formulas where if I want the horizontal and vertical components A and B to express the vector, well, if I know the magnitude and the angle theta, then I can use the right triangle relationship we showed in the beginning, and I know that A is the magnitude times cosine of the angle. That's going to be the x value, and B is going to be the magnitude times the sine of the angle. That's going to be the y value. And therefore, the AB coordinate point can be expressed where we can calculate A and B using these relationships, using u cosine theta and u sine theta to determine the A and the B values. And so therefore, given the magnitude and the angle, we can express u as AB using this relationship. So let's do that in example 2. So in example 1, we were given A and B, and we found the magnitude and theta. And now in example 2, we are given the magnitude and theta and direction angle theta. And we're going to find the horizontal and vertical components, namely the A and the B value, to express the vector that way. So they just plug into the formula. So we know A will be equal to the magnitude of W times cosine theta. And so the magnitude is 25. And we can take cosine of the theta 41.7 degrees. And that tells us that A is approximately 18.7. That's the x value of the terminal point of the vector. Similarly, B would be absolute magnitude times sine theta, which gives us 16.6, and B is sort of the y value of the coordinate. And so then we can express W as the vector AB with 18.7 for A and 16.6 for B, just by plugging into these sort of formulas for the the horizontal and vertical components of the vector. So now we have vectors in this XY coordinate system in this sort of ability to express them algebraically as X and Y values of their terminal point. And we can go from either direction. If we have the angle and the magnitude, we can express the XY coordinates of the point or the AB coordinates of the vector. And if we have the AB coordinates of the vector, then we can convert those into the magnitude and the theta value of the vector. All right, so now we start to have some fun writing vectors in the form AB. So they're now just having us practice that, write each vector in the figure in the form A, comma B. And so what we see in the picture is that the two vectors are both, well, we have U, V, and W, that the three vectors are expressed with angles and magnitudes. So looking at U, we have a magnitude of 5, and we have an angle of 160 in the picture. So as we just did in the previous example, we write 5 times cosine 60 and 5 times sine 60 to get the AB coordinates of the point. And so cosine 60 is 1/2 and sine 60 is √3/2. So when you evaluate those and multiply by 5, you get this point, 5/2 and 5√3/2. Then for the V vector over here, we can see the angle to get to V is 180 degrees, and V has a magnitude of 2. So multiplying 2 times cosine and sine of 180 gives us the point -2, 0. And we could see in this case more comfortably, since V is just riding out on the x-axis in the negative direction for a length of 2, that it's going to land -2 to the left with a height of 0. But nonetheless, the formula substantiates that by plugging in the angle and the magnitude and getting us that exact result. And then one that doesn't come out quite so nice and friendly in terms of the angles or the final position is W. And we see W has a magnitude of 6 and an angular rotation of 280. So just plugging those in, magnitude of 6, sine and cosine of 280, in the other order, I guess. And we get the approximate finishing coordinate points of angle V, of vector W, to be an A value of 1.0419 and B value of -5.9088, just by plugging in cosine and sine of 280 into the calculator. All right, so problems like this hopefully will be pretty straightforward, especially if you're given theta and magnitude. Then again, we just use these nice little formulas, magnitude cosine theta, magnitude sine theta, and you get AB. And so we had 3 little practice sessions for that in example 3. So now let's go back to our operations that we did in 7.4. And so we looked at vectors and we talked about adding 2 vectors together, and it involved sort of graphically attaching the second vector to the end point of the first vector and then drawing a new vector from the beginning of the first to the end of the second. Well, algebraically, it boils down to addition, which is why we want to look at vectors algebraically so we can add vectors using algebraic addition. And so if I have the vector AB and I add to that the vector CD, well, instead of trying to visually attach one to the other and do something graphically, we can literally add the X components together and the Y components together to get the resulting sum of those 2 vectors. Much simpler, much nicer. So AB plus CD is A plus C, comma, B plus D. And similarly, for scalar multiplication, we can imagine that when you multiply a vector by 2, you get the same directional vector, but the magnitude just increases by 2. And happily, the way that you can do that with scalar multiplication of a vector is to literally just distribute the scalar multiplication to each component of the vector. And so K times the vector AB is just KA, comma, KB. Very nice. And so algebraic addition and scalar multiplication, luckily for us, basically happens in the simplest algebraic way possible. You translate the addition of the vectors to the addition of their components, and you translate the scalar multiplication of the vector to multiplying each component by that scalar number. And then similarly, if you have a vector u, which is equal to a1, a2, I don't know why they would do that instead of just putting ab, then the opposite of that vector, which we now know from graphical interpretation is the same magnitude vector pointing in the opposite direction. But to do that in terms of coordinates, you just change the sign of both of the coordinates. So if you had a1, a2, then you have negative a1, negative a2. And again, when you put a minus in front, that doesn't mean you end up with a negative result. So for example, if you had the vector 2, negative 1, I'm sure we'll do an example in a minute, if that was equal to u, whoops, then the opposite of u would be negative 2, but the negative 1, when you change the sign, becomes a positive 1. So you just change the sign of both coordinates and you get the opposite vector. And then, like we did graphically in 7.4, the way we do subtraction of two vectors is we think about subtraction of two vectors by adding the opposite vector. We basically change the sign of the second vector and then do addition. And what that will end up translating to is adding the opposite numbers of C and D. And that's the same as going back to subtraction. So if you have AB minus CD, you just do A minus C and B minus D. You just subtract the component values, subtract the X values and subtract the Y values. So subtraction of vectors will just mean subtract the X's and the Y's. It's ending up to be very simple. We had to go through some definitions and some algebraic procedures to justify this, but in the end, happily you add, multiply scalar, and subtract vectors in the way that you hope you would, just with each of the components for X and Y. So let's practice that. And I apologize in advance when I got to this slides originally, all of the little vector angle versions, angle sort of parentheses around the vectors were all little question mark boxes. They worked before, but then they didn't on a bunch of these slides. So I just kind of erased the little boxes and drew in the vectors. So I apologize for that, but nonetheless, hopefully it'll make it much better than it was before. So they give us a couple of vectors. Let u equal negative 2, 1, and v equal 4, 3. Then u plus v, negative 2, 1 plus 4, 3, is just negative 2 plus 4 and 1 plus 3. Add the x's, add the y's, and you get your answer, 2, 4. And we can see in the image what each of these results would look like. And we can also confirm in the image that if we drew the parallelogram that we did back in 7.4, that this process of just adding the x's and adding the y's does give the vector for the summation of u and v that we were looking at graphically in 7.4. It just does it in a much easier way when you look at the ending coordinate values of the vector. And so I could think that I got the parallelogram and got the addition of the two vectors by looking at the diagonal like we did in 7.4, and we can confirm that that's just what you get when you add the x's and the y's together. So, but when you're actually doing the problems now, it's going to be nice and easy because you just add the x's and the y's. So problems and the homework and stuff should go very, very smoothly when you're just adding vectors if you just add the x's and the y's. Similarly, if we wanted to multiply by the scalar negative 2, so they give us, well, they give us two vectors here actually, so they're probably gonna do a couple examples with it. But the first vector u, which is just 2, negative 1, they say, all right, what if I take that and I multiply it by the scalar negative 2? Well, again, that means you take the negative 2 and you just distribute it to the x and the y values of the vector. So they multiply negative 2 times the x value of negative 2, and they multiply negative 2 times the y value of 1, which I had to redraw there, much worse, of course. And negative 2 times negative 2 is positive 4, and negative 1 times 1 is negative 2, and that gives me the scalar -2 multiple of u. And they show in the image if u was the blue vector and the result is 4, -2. Well, if you plot the point 4, -2 and draw the resulting -2u vector to it, you'll see that you just went in the opposite direction with twice the length that you had before, which is what we would have expect to have happen from 7.4. But now we can carry that out much more easily by just multiplying the scalar times the x and the y values of u. Okay, and more examples. So in this case, we're going to multiply by scalars and do subtraction. This basically allows us to do what we in algebra would have called a linear combination of any two vectors. And so you may recall from algebra that they did linear combinations of equations and things like that. And now we're going to do that with vectors. So again, these same two vectors, u is -2, 1 and v is 4, 3. And now we're going to not only multiply each of those by a scalar, but then subtract the result. So 3u minus 2v, we would first write out the vectors in component form, replacing u with its AB coordinate value, -2, 1, and v with its AB coordinate value, 4, 3. And then each of those is multiplied by 3 and -2, and then we add them, or multiply by +2 and subtract, means the same thing. So again, to do that, we get to just simply distribute the 3 to the components of A, and distribute the 2 to the components of, I should say, u, and can distribute the 2 to the components of v. And so then we get these results, -6, 3 and 8, 6. And then we do the subtraction by subtracting the x's and the y's. And that leads us to our result of -14, -3. And if we visualize what's going on graphically, as we would have had to do these operations in 7.4, we can see the multiples shown. So they don't even show the original u and v, even though they did that back in the earlier example. But if you double v, you get the, you double v, you get that left blue vector. And if you triple u, because u is a teeny little vector, it ends up there. And then we would take the opposite of 2v, since we want to subtract that, and that gives us this. And then we add the opposite of 2v to 3u by imagining a parallelogram here and drawing the diagonal, and we get the result of 3u minus 2v. And we can see that the place it ends up are the coordinates that we get when we do it algebraically up above, -14, -3. So you can kind of compare the graphical process you would have to go through from 7.4 to the result we get with the more simple algebraic process, and see that you get the same thing, and see that what we're doing here algebraically is the resulting same thing we would have been doing graphically before with the vectors. Okay, so that's the place where they finish reviewing scalar multiplication, addition, subtraction that we did in 7.4, and doing it all now algebraically, which hopefully makes it much easier, and that we can even do more complicated, like linear combinations of a couple of vectors. So now with these vectors, we're going to, in algebra, we're going to introduce some components that we use for further work with vectors. And again, we're finishing in vectors in trigonometry because vectors are used in physics later and other math classes later in calculus, and also in other math classes in the future. And so one key element in this work later is called the unit vector, which is the vector that has magnitude of 1. And well, so first of all, sorry, we're going to define two things. A unit vector specifically is any vector that has a magnitude of 1. So unit meaning single, a length of 1. And then we define these specific unit vectors in the x and y direction. And so I is the unit vector in the x direction. And then j is the unit vector in the y direction. And so you can see them graphed here. You just have these little length 1 vectors pointing to the x to the right for I and pointing straight up for j. So we are going to define these things because it helps us basically to imagine how vectors that end at a particular point, like 2, 3 or something like that, can be expressed as a linear combination of I and j. So it will seem a little silly to make this breakdown, but we're just going to introduce it now, and it ends up being sort of important later. And so they do that. They say, all right, let's say you have any vector AB, then you can express that in a form of a linear combination, meaning some summation of scalar multiples of I and j. Well, namely, since I is 1 unit in the x direction, then if you instead went, as they're doing in this example here, 3 units in the x direction, then that would be 3 spaces over, or 3 times I. And if you had lifted up to the height of 4 in the y direction, then that would be 4 times j. And so if we have u, in this case, equal to 3, 4, then they show that that point 3, where u terminates at 3, 4, translates to 3 i's and 4 j's, and so that u could be written, as they do up here, as 3 times the vector 1, 0, whoops, there we go, plus 4 times the vector 0, 1, and then that translates to here, or I'll do it down here, 3 times the I vector plus 4 times the j vector. Now, of course, it doesn't really look like we're doing much of anything, and I understand that completely from the perspective of a student looking at this for the first time. You just took the vector coordinate, you just took the terminal point 3, 4, and then you translated that into a terminal point of a vector by putting vector brackets around it instead of parentheses. So that's step 1, to write 3, 4. And then after that, you just put the 3 and the 4 in front of the letters I and j to write it in terms of these little unit vectors for I and j. So you're just taking the 3, 4 and kind of writing it 3 different ways. And initially, that's all you're really doing. So there's no reason to feel that this makes sense to you right away. Why are they going to all this trouble? Why are they bothering to write it that way? Again, it's just for preparation for future work, and we're just giving you introduction now. So here's sort of the formal combination of this. Oh, and I forgot to write my little boxes around these, so I'll just do that right now in front of you. This is what I tried to do before. If v equals the vector to AB, then V can be written as A times I plus B times J, where I is, as we defined above, the unit vector 1, 0, and J is the unit vector 0, 1. So you can just immediately translate the vector coordinate point AB to A times I and B times J. Why would we ever want to do that? That remains to be seen later, but we can do that. All right, so now we're going to get to the end of this final section by defining a very important operation for vectors called the dot product. This is very important and is used a lot when you work with vectors in whichever time you might work with vectors in the future. So the dot product of 2 vectors, and we're going to say u and v are those vectors, and u is AB and v is CD, is denoted with sort of like this little square or a fat dot, or sometimes it's written a little bit different ways. So let's look at what they have here. They have u dot v with kind of a thick dot there. I don't know, it doesn't actually look thick enough there. Sometimes it's written as u dot v with kind of big dot or a square dot as they try to write, and it, as they try to write here, and it's read U dot V, and is given by the following. So, so I want to stress here that the result here is a number, not a vector. So U dot V takes two vectors, U and V, and does this dot product kind of special multiplication together. And the result is not a vector, it's a number. So we had a scalar number times a vector, in which you just distribute the k to the components of the vector, to a and b in this case. So that's a scalar number times a vector, and you get a vector. But when you do a dot product of a vector and another vector, and it kind of looks like multiplication, you end up with an actual number. You end up with a scalar value, not a vector, like a 5 or a 7 or something like that. And so this little formula tells you how to get it. And so you can note that the AC is the product of the x values, and the BD is the product of the y values of the vectors. And then you add them up. So you multiply the x values together, and you multiply the y values together, and after those products are taken, you add up the result, and the number you get, that's the dot product. You can just sort of see the formula here, but think about it as the x's times the y's added up. All right, so then we just practice using this operation. So the dot product of 2, 3, and 4, -1 is the x's multiplied together and the y's multiplied together, and then you add them up. In this case, 2 times 4 plus 3 times -1 gives you 5. But note, this is a number. This is not a vector. So we took a dot product of a vector, and we get a number. And you just use the formula, x's multiplied together, y's multiplied together, add them, and that gives you the number. Example 2. So I would do 6 times -2, which they do here, and I would do 4 times 3, which they do here, and I'd get a -12 and a +12, and I would add those up, and in this case, we get a 0. Now, you can actually do these things on a graphing calculator and things like that as well, but initially, it's pretty straightforward to just do it yourself and get used to the idea of what it's doing. And the big thing is to sort of structurally start to get used to the idea that a vector dot product with another vector ends up just giving you a number. That's not a vector. All right, so having looked at all these things, they now give you a bunch of different properties. And so this is something that ends up being important later, but for us, we'll just practice these a little bit. You'll have some problems that ask you to reference this list, basically. Keep in mind, for all of our examples, you're welcome to use any notes that you have. So you could just put this in your notes in case it's ever referred to and shows up as problems. But there are parallels with what we're doing here to things from algebra before. So we can at least look at that from before, and maybe you'll remember some of the names, or that you can compare these to things from before. So here we have dot product being used, right? This is the new thing, the dot product we just looked at, which is not like normal multiplication because we have a dot product of vectors giving you a number. However, this ability to say that u dot v is equal to v dot u, that was something we did look at for regular multiplication in algebra. This was called the commutative property of multiplication in algebra, that basically 5 times 2 is the same as 2 times 5. Well, it works the same way for the dot product of vectors. So if you got comfortable with that ability that you could reverse things around when multiplying numbers, you can do the same thing with the dot product of vectors, and you can translate that idea to the dot product. Similar in this second one, just to help wrap our minds about what all of these juggled letters is telling us. Well, you may recall with values of numbers that 2 times x plus y, that you could use the distributive property for multiplication to get 2x plus 2y. And that ended up something you did in algebra a lot. Well, we have the distributive property again here, but in this case, it's for the dot product kind of multiplication of vectors over the addition of vectors. And so you can basically distribute the dot product of u to v plus w by doing u dot v plus u dot w. But again, in the end, in this case, this will end up just being a number, and there won't be a vector left anymore. And if the w was on the right side of the summation, then you could kind of distribute backwards, if you will, as long as we're going to be careful and keep the order the same for the moment, so that u plus v dot product with w is u dot w plus v dot w. And then, of course, because of the first property, you could even reverse the order of the w and the u and the w and the v if you wanted. But this is basically the distributive property sort of from either direction, from the left or from the right. And they're just spelling this out. But if you kind of think of it as the distributive property and remember that the dot product is commutative, it'll look like algebra problems from your past, hopefully. And so in this case, this sort of shows now scalar multiplication being allowed to be brought in either way. This translates from algebra. There used to be a property where we had, if you have A times B, and then you multiply that by C afterwards, that's the same as doing the B times the C first, and then multiplying by the A afterwards. So this was called the associative property of multiplication. Again, these were all numbers before. Well, now they're kind of mixing that together with scalar multiplication and the dot product. So they're saying if you have the scalar multiple k times u that you dot product with v, then you could instead save the scalar multiplication of k and do the dot product of u times v first and then multiply the scalar afterwards. Or you could also move the k over and do the scalar multiplication of k times v first, and then go back and do the dot product with u. But in any order that you do that, you always get the same answer in the end. And I would point out that you can remember the answer for all three of these is not a vector, it would be a number in the end. So you're going to get the same number in each case. And then lastly, there's kind of a simple thing. If you have a scalar multiple of 0 times a vector, you get a 0. Now they're showing this with the dot product symbol. So this is kind of like the dot product of the 0 vector gives you a scalar of 0. And so that's sort of the little detail to take note of here. But the same thing is true if you do a scalar multiple of the scalar number 0 times a vector, then you still get a 0. But in that case, you get the 0 vector. And then finally, if you dot product a vector with itself, which is kind of interesting, that's going to give you a number. Well, you could kind of imagine that real quickly. What does that look like? That's AB dot product with AB. Whoops. And so again, the dot product is the x's multiplied together, the y's multiplied together, and that added up. So that would be a squared plus b squared. And they're showing here that this is the square of the magnitude of u, because we remember the magnitude of u is the square root of a squared plus b squared by the Pythagorean theorem. And then, of course, if I were to square that, I would just get a squared plus b squared, which is u dot u. So anyway, they're pointing out that if you dot product a vector with itself, you get the square of the length or the magnitude of that vector. So these are all properties of the dot product and how the dot product defined up here, this little formula, the sum of the x's and the y's multiplied together. That this leads us to all of these things that look like things we've done from before in algebra, like the distributive property and the associative property and other things in the commutative property. But anyway, so these are things to think about, and we're not going to work with vectors enough for all of these things to be completely comfortable. So that's why I recommend that you take note of this little list of properties of the dot product in case they are asked about, or you have to do some sort of a manipulation in the problems that we actually do for this class. All right, and then last but certainly not least, or used toward the last big thing we want to look at, is the geometric interpretation of the dot product, which basically just gives us a little equation in vectors that results in the cosine of an angle. So let's just take a look at what it says. If theta is the angle between the two non-zero vectors u and v, again, imagine those sitting at the origin in terms of where they begin and finishing at some coordinate points A, B, and C, D, that the cosine of the angle between the two vectors, so maybe we'll just, they'll probably draw it in a picture in a second, but imagine that we have these two vectors. We have u and we have v, just to think about this graphically as well. And then we have some angle between them, theta. Well, then the cosine of that angle between any two vectors can be found by taking the dot product of u and v and dividing by the product of their magnitudes. And again, this is where theta is between 0 and 180 degrees. So we don't want to have rotating all around a bunch of times. Just if I have two vectors, if they're pointing in opposite directions, that's 180 degrees. And if they're pointing anything less than opposite directions, then we don't go the long way between them, we go the short way between them. So I would not be doing theta like this way or something like that. It's always going to be the shorter angle theta between the two. So that's why they say theta is between 0 and 180 degrees. In any event, so that whenever you have these two vectors, the angle between them, the short way, cosine of that angle is the dot product divided by the product of the magnitudes. And that gives us a little formula for cosine of theta. And so we then practice that. So if we have a u and a v as given here, 3, 4, and 2, 1, we can find the angle between those vectors by using this relationship and taking the inverse cosine. And remember, inverse cosine produces values between 0 and 180. So it'll always give us the angle we want between those two. So they plug in and they say, all right, 3, 4, and 2, 1, and they take the dot product in the top. And then they say, we're going to have to multiply the magnitudes on the bottom. And then we have a formula for the dot product, so add up the product of the x's and the y's. And then on the top and then on the bottom, for each one, you have the square root of a squared plus b squared, where those are the x and y coordinates of the point, or the a, b coordinates. And they just do the arithmetic and they come up with 10 in the top and 5 root 5 in the bottom. And you could simplify that or play with that, but you're going to bother to do that because then they're immediately just going to take the inverse cosine of that result. So there's no reason to simplify that fraction or anything if you're just going to put it into a calculator to see what theta would be. And they get 26.57 degrees. And so this is very nice. Given any two vectors, you can imagine that if you have them, there's some angle between them, and this gives you a little formula to find the angle between any two vectors from this relationship. Give it a bump. So here's another example. So in this case, they have 2, -6, and 6, 2. And so you could kind of imagine these vectors just to sort of see why they gave these, they look kind of similar numbers. So if I have 2, -6, that's like down here somewhere, 2 to the right and -6 down. Whoops, that's not a parentheses, it's supposed to be a vector. And then similarly, if I go to 6, 2, so that would be 6 to the right and 2 up. So I have the vector here, and I have the vector here. And I can kind of imagine that if this is 2 and 6, and this one, the other one is 2 to the right and 6 down, that you can kind of visualize this might be a 90-degree angle. But you can confirm that by plugging those vectors into the formula we just did. And you end up, when you do this arithmetic, especially because of the dot product in the top, that you get a 0 for the dot product in the top. So then the magnitude of the vectors on the bottom doesn't matter. 0 over any number is going to give you 0, as long as the bottom's not 0. And the inverse cosine of 0 is 90 degrees. So that confirms that there's a right angle between these two vectors. So this is a nice example, 6b, to illustrate that. And so finally, we have for angles between 0 and 180 degrees, the cosine theta is positive. We just know that from cosine theta is positive or negative when it's less than or equal to 90 degrees. So they sort of summarize that in this table. I just said that very, very badly. So let's look at this nice table instead. So if we're talking about the angle between two vectors, then we know if the dot product is a positive number, that it will be acute, less than 90 degrees. If the dot product is 0, as we just saw in example 6b, then you have a right angle between the two vectors. And if the dot product is negative, that means the two vectors are spread apart by more than 90 degrees, between 90 and 180, and that's an obtuse angle between the two vectors. So it's a nice quick summary we can do by just looking at the formula up here, by basically taking a closer look at just the dot product, not worrying about the size specifically, but if you just look at the dot product and think about, is that going to be positive, 0, or negative, then we get these three results that they just described. Then the angle would be acute, or right angle, or obtuse. Just by focusing on the dot product in the formula, because you know that those are the results of the angle you would need for the cosine to come out positive, 0, or negative. So that's a nice little summary to finish with. And then what do they have at the end, like a note or something? Yeah. And so if the dot product is 0 for two non-zero vectors u and v, then you know they're at a right angle, and that those are perpendicular or orthogonal vectors. So if you have any two vectors, knowing that you make a right triangle if you connect their ends together is a very nice thing to be able to tell by quickly just doing the dot product. Again, dot product, take the product of the x values and the y values and add that up. And if you get a 0, those vectors have a 90-degree angle between them. That's a very nice note to finish with. And that means that they're perpendicular, or orthogonal is another word for perpendicular vectors. And that is where we finish up today. So lots of information, but hopefully the little procedures are pretty easy to follow, and the problems using these operations on vectors will be pretty easy to do. And so hopefully that's a more comfortable way to finish the class than a bunch of trig identities and equations that are complicated and challenging. So congratulations to getting to the end of the material for the class. Hopefully this will help. Keep up the hard work, and I hope you all finish well. Have a great day.